Hello everyone, let us continue our discussion on reinforced concrete design. We are in the 6th week and this is our 4th lecture, and in this lecture we are going to go through the special provisions that is made in a dedicated code. As you can see on your screen, this is IS 13920, and this code is for ductility detailing of reinforced concrete structure subjected to seismic forces, right? So the main point to be noted here is this ductility detailing. Okay. Now, as we progress, we'll see why it is required and what are the provisions that this particular code recommends us to follow. Now, if you recall, we discussed the design of a singly reinforced beam section. So if you have, say, this is the section, then our first task was to find out neutral axis, right? And then the concrete above the neutral axis, which is in compression, that we consider, but the concrete below the neutral axis, we ignore, we only consider the steel, right? During that discussion, we also developed what is called under reinforced section. We developed the mathematical models for this under reinforced section, and there we recommended the design of under reinforced section and not the other options. What we had is over reinforced section, right? This we did not recommend. However, under reinforced section we prefer. In between these two, there was something called balanced section. Let us not focus on that for the moment. Our point of view now is under reinforced section, and the reason we recommended under reinforced section is that in this design concept, we have some time before the before the section, RCC section collapses. And when we go for this over reinforced section, here because concrete fails and it is not good in tension, then obviously it experiences a brittle failure, and that doesn't give much time to the user as time to take some action before failure can occur. Whereas on the other hand, in case of under reinforced section, we have ductile failure, right? And this is very important. When we have ductile failure, then we actually do not have a sudden failure, and that's the reason it is preferred more than over reinforced design of beam section, right? Now, once a section is designed, for example, say this cross section, as you can see on your screen, and then we leave the structure to face the earthquake, which is again time dependent loading. And during that process, what happens, this a section which is a part of the section which is under tension may be under compression, and vice versa, right? So that's the reason during earthquake, every structure, for the time being we are focusing on buildings, but every structure is exposed to reversed cyclic forces, right? And this is a point of real concern. Okay. Now, as I have already explained that under reinforced section is preferred, the RC buildings which are actually designed as per given provisions, they also collapse. And in fact, the history shows that those buildings which were designed earlier as per the codal provisions, they collapsed all of a sudden, and the reason was lack of ductility, right? So that's the reason even if we design a structure, beyond that, when we go for detailing, this code is extremely important, and the provisions here actually helps us to incorporate ductility detailing, and during the failure, it really helps. Now, how it helps ductility detailing? It enables the members to deform in a controlled manner, dissipate energy, and avoid sudden collapse. So this is the main feature that we are going to bring in structure when we detail it, right? Now, before we go into the details of what is ductility detailing, let us just go through some observations. As you can see on your screen, we have different types of failures that is experienced in the past. Now, there are different types of failure. As you can see, there is a shear failure, then joint distress, then buckling, inadequate anchorage, and there are many other types of failure. But one thing you can see is common in all this. For example, here you see excessive deformation of the steel. Right here you can also see there is a excessive deformation of the reverse. This is the reason we need to provide a ductility detailing. But before we go into the details, the question automatically comes in our mind: what is ductility? Now, it is the capacity of a structural member to sustain inelastic deformation. Okay, this is important. Recall, for example, when we consider rebars, our strength at the point of yielding is Fy, and we consider 0.87 of Fy as the design value, right? Now, beyond this, what happens? We experience a elastic deformation. And if you recall the schematic diagram of the stress strain behavior of steel, then we have initially a straight part, then it goes up, and then there is a valley part, and then finally it breaks. This is a schematic diagram of stress strain of steel. Now, during this part, what happens? There is no significant change in stress, but a significant change in strain, as you can see here, right? And during this period, it undergoes a large deformation without any significant change. And of course, because there is no significant change in stress here, it is still not at the point of collapse, as you can see. And this deformation is really helpful for the users because they get some time to evacuate the structure and come to safety before the structure actually breaks at this point. Now, in reinforced concrete frames, ductility actually is achieved primarily through flexural yielding of beams, proper confinement of concrete. This is extremely important. Because if you go back to this, you see, for example, this failure where you have this column section which is bulged, and you can see the confinement between the concrete and this bars, it is lost, and you can see it has actually bulged. Okay, here you can see, okay, this is more prominent here. So, confinement of concrete is extremely important. Then prevention of premature shear and bond failure. This is also very important because if the bond between the concrete and rebars are failed, then that also leads to the complete collapse of the structure. Then obviously the buckling of the bars, right? Now here at this moment, we should distinguish between strength and ductility. Strength is the ability to resist load, while ductility, as I explained here, is the ability to undergo large deformation without losing load carrying capacity. So here you see the stress does not change much while there is a significant deformation. So this is the ductility, which is totally different than, for example, say yield. Yielding is somewhere here, we call it Fy, and then we use this expression to design the structure and use the design strength. So there is a distinction between strength, which is the ability to resist load, while ductility, it is the excessive deformation that a material undergoes without significant change in load carrying capacity, right? Okay, so now let us quickly compare the brittle failure and ductile failure, and then we will see how we can bring in this concept as per the code that I have already shown. Now, brittle failure, it is a sudden failure. It doesn't undergo large deformation. This is important. Because it is a sudden failure, there is not much warning. There is not much time between the structure reaching to its collapse point. Often governed by shear and bond, and leads to rapid collapse. This is important. Okay, because there is no warning time, we experience a rapid collapse. Compared to that, ductile failure is gradual. So from yielding to the failure, we can see how this stress strain progresses, and then without significant change in stress, we have large deformation. So large deflection is visible in this case. Then for this yielding, redistribution of forces is possible. This is extremely important. Redistribution is possible because if one section yields, then the stress is redistributed in a frame where we have different stiffnesses connected to a point, then provides time for evacuation. This is important. This is the reason again and again we come back to this detailing as per Indian codal provisions. Okay. Now, what are the objectives we want to achieve through this ductility detailing? First of all, obviously prevent collapse. Then we get sufficient time and large deformation so that we can prevent collapse. Perfect life safety, because this is important. If we design a structure and leave it, that is not the main purpose. Serviceability is also equally important. During an event, the users of the structure should get sufficient time to react, and in this ductile failure, that is possible. Now, because we prevent collapse and through large deformation, the structure is still there, then we can actually have the scope for repairing the damage. Okay, we can rehabilitate the structure and bring it back to its operation. We have better energy dissipation through this process, and of course, due to this reason only, we have provided the capacity to withstand large deformation. Now, let us first go through the ductile detailing of beam and what the code says. In beam, the factored axial compressive stress does not exceed this value of 0.08 FCK. So that is the first requirement. Then beam shall preferably have width to depth ratio more than 0.3. So if we design a beam, if this is B and D, so width to depth, so B by D ratio should be more than 0.3. Because then we'll get a better beam action. Obviously, we should not have a very large value of D, because in that case, we may encounter with a deep beam, which we'll separately discuss in the following weeks. But we should not have beam like this, okay? Because in that case, it behaves like a plate and the behavior is completely different, okay? Beam shall not have a width less than 200 millimeters. So it should not be less than 200 millimeters. Now, obviously, you can easily sense that if B, we keep it as 200, then we can evaluate the minimum value of D from this relation, right? Now, beams shall not have depth more than 1/4 of the clear span, okay? Now, if we have a clear span L, then D should not be more than L by 4. This may not apply to floor beams frame staging of elevated RC water tank, but this is a special case. For the time being, let us not focus. The point is this guideline, and again you see these are the most important guidelines to ensure ductility in the structure that we design. Then width of beam BW shall not exceed the width of supporting member C2 plus distance on either side of the supporting member equal to the smaller of A and B. What is that? Width of the supporting member C2 or 0.75 times the breadth of the supporting member C1, right? So you can see the diagram is here. We have C2 and C1 here. So the beam width BW should be selected accordingly to this guideline. Then transverse reinforcement for the width of the beam that exceeds the width of the column C2 shall be provided as shown in figure throughout the beam span including within the beam column joint. Now you can see the detailing here, this detailing, and here we have to follow to ensure that proper reinforcement are placed along with longitudinal and transverse bars with proper confinement within the beam and column section. The idea is it should transfer load from beam to column, and particularly when there will be large deformation, this load transfer should be proper. Okay. Now, just recall, if we have a frame structure like this one, earlier we discussed, say there are some loading here, we discussed the design of beam at this section, then design of column, then we design the column at these sections. But now we focus at the corner, at the junction where we have the load transfer between the beam and column, because during this large deformation, it is this section which is critical and that will efficiently transfer, and if the situation arises, redistribute the moment among the joints. So next is beam longitudinal reinforcement. From the ductility detailing point of view, beams shall have at least two 12 millimeter diameter bars, each top and bottom face. Now, recall again, when we design this section, we consider, say, this section is under compression. So we do not consider steel there and we consider steel here. This code says, this guideline says, we have to have at least two 512 bars. And the minimum longitudinal steel ratio is given here, which is 0.24 times square root of FCK by FY. So this is the additional requirement we have to check beyond the design that we have already discussed in detail in our previous lectures. There, if you recall, we discussed AST minimum. But now, from the ductility detailing point of view, we have, this is again important and we have to ensure that this is followed. So maximum longitudinal steel ratio, rho max, provided on any face at any section is 0.025. Then longitudinal steel on the bottom face of the beam framing into a column at the face of the column shall be at least half the steel on its top face at the same section. At exterior joints, the anchorage length calculation shall consider the bottom steel to be tension steel. Now again, if you recall, we have already discussed that this junction is now important, and if you have also intermediate junctions where column meets beam and from beam load is transferred to the column, these junctions are extremely important and accordingly we have to follow these guidelines while detailing, right? And recall, if you have a beam coming into column, so these bars we have discussed in detail that these bars should be sufficiently anchored within the column itself. We cannot leave the bar here. We have to check the development length and accordingly we have to anchor it within the column. And in fact, we will see the detailing in a minute, further details of this detailing. But for the time being, longitudinal steel in beam at any section on top or bottom face shall be at least 1/4 of the longitudinal steel provided at the top face of the beam at the face of the column. When the top longitudinal steel in beam at the two supporting column face is different, the larger of the two shall be considered, right? So this is again important. When you have a frame structure, then top face of the beam, we have to see how much is the steel requirement, and then depending upon the location, we have to follow this guideline to ensure that we have significant amount of steel reinforcement for efficient transfer, particularly during large deformation. At the exterior point, top and bottom bars of the beam shall be provided with anchorage length beyond the inner face of the column equal to the development length of the bar in tension plus 10 times the bar diameter minus the allowance for 90-degree bends. Again, it is the same point I have already discussed, and during the discussion on development length, we actually saw how these development lengths are evaluated, and then what are the impacts of hooks of different angles, and then accordingly how to design it. So This clause says that this is extremely important. We should have sufficient development length, which I have already explained, at the junction of beam and column. Now, next is splicing of longitudinal reinforcement. Again, if you recall, we discussed the splicing, location of splicing. So, closed links shall be provided over the entire length over which the longitudinal bars are spliced. Okay. So, the links that we provide, we should not have open links. The spacing of these links shall not exceed 150 millimeter. Okay. So, we should not have a spacing which is more than 150 millimeter. Then the lap length. So, if we have, recall, we have bars of a particular size. So, when we design a beam, it may so happen that we need to connect two bars. Okay. Then we provide this is the lap length. So, when one bar is placed side by side to others, so the lap length shall not be less than the development length of the largest longitudinal bar. Okay, so here if you have, say, this is the bar of say 12 diameter and this is say 16, if that is the situation. So largest diameter bar will dictate the development length and we should have the lap length which is more than this development length. Recall sometimes we use connectors also to connect the bars, right? And we normally avoid welding because welding sometimes damages the cross section. Okay, so if you have two bars, they are not welded together. Okay, welding is not recommended because it may damage part of the section during welding process. So sometimes coupler is used. The common practice is lap length, and for that we have this guideline. Not more than 50% of the area of steel bars on either top or bottom face shall be spliced at any one section. So what it says that if you have a section, say this is the section, so you have top members and bottom members, and if you apply splice more than 50% in a single location, you should not approach. So in that case, you stagger it. So you have a splicing here and then you have another splicing at some locations, but it should not go more than 50% at a particular location. Now, lap splices shall not be provided within the joint. Okay, this is important. Within a distance 2D from the face of the column, within a quarter length of the beam adjoining the locations where flexural yielding may occur under earthquake effects. Now, again and again, you see it talks about earthquake because that's the input that brings in reversal of stresses, right? So, that was the guideline for longitudinal reinforcement. Then now comes the transverse reinforcement. So, for transverse reinforcement, only vertical link shall be used in beams. This is important. Okay. Recall when we discussed this links, the design of this links, we also discussed this is the vertical link and this is the inclined links, right? So only vertical links shall be used in beams. Okay. The minimum diameter of the link, this we discussed, 8 millimeter. So phi is 8 millimeter. Hook of links and cross tie shall engage peripheral longitudinal bars. Okay, this is important because that's the sole purpose of providing links and ties, right? Consecutive cross ties engaging the same bar shall have 90-degree hooks in opposite side. Okay, so consecutive links, this is another important feature. You can see they are hooked at the corner. So 90-degree hooks on the opposite sides, right? If a slab exists on one side, the 90-degree hook shall be placed towards the slab side, because if we have, say, this is the slab and if this is the beam and these are the beam reinforcements, then obviously if we have a transverse reinforcement, we can provide the hook here, but that is not recommended. The reason is because this is a discontinuous edge, it is always better to provide this, and here we will get more concrete to anchor it properly, right? Rather than at this corner where we have only the clear cover to deal with the anchorage. of these bars, right? So in that situation, we'll provide these hooks here. Then the first link shall be at least at a distance not exceeding, 50 millimeter from the joint face. So here you can see this is the joint face, and from this we have the first link here, and this link is at a maximum distance of 50 millimeters. So we have to have as close as possible. Sometimes it is difficult because we have to put the shuttering for this column, and that's the reason it is difficult to bring in here, but preferably it is as close as possible to the joint face. Closely spaced links shall be provided over a length equal to 2D on either side of the section where flexural yielding may occur under earthquake effects. So here you can see it is marked. Okay. Recall these are the joints, so we'll have hogging moment here, and then obviously this region during earthquake may see the change in stresses, and therefore this region is extremely important, and we have to accordingly place the shear reinforcement there. Over the remaining length of the beam, vertical links shall be provided at a spacing not exceeding d by 2. So if this is d, the spacing in no case should exceed this d by 2. Okay, as you can see here. Now, spacing of links over a length of 2d at either side of the beam shall not exceed d by 4, 8 times the diameter of the smallest longitudinal bar, and 100 millimeter. Okay. So during this detailing, we have to keep in mind that the spacing between these two bars should assure this guideline. Right. Next is extremely important. Shear force capacity of a beam shall be more than larger of these two. Okay. Factored shear force as per linear structural analysis, this we have covered in our previous discussion on design against shear. So basically we do a linear analysis, we find out the shear force at a particular location and design that. Now, in addition to that, this is something new and very important. Factored gravity shear force plus equilibrium shear force when plastic hinges are formed at both ends of the beam given by, this is the equation. So if we have a beam which is fixed, here we have column at the two ends, right? Then we have dead load plus live load, this load combinations with appropriate load factors. Then sway may occur, so the frame may sway on either side. So during sway to right, we have, these are the additional requirement for shear force, and when it is swaying on the left, we have, this is the value of the shear force. Where from we get, we have to quantify this support moments. Okay, as you can see, these are marked here, these support moments and support forces. From that, we need to recalculate. The design shear force demand at any end of the beam shall be the larger of the two values for two different sway cases. So we have two different sway cases here, and then we have also linear analysis, then plus this analysis. So larger of this value we should consider when we design the reinforcement against shear. Now, for that, let us consider a problem. So a beam with a section of, you can see 300 millimeter by 500 millimeter and a clear span of 5 meter spanning between two columns. It is subjected to a uniformly distributed load of 50 kilonewton per meter throughout the span. The reinforcement provided in both support sections are shown in figure. As you can see, complete detail of reinforcement is given here. Calculate the design shear force considering probable moment capacity at beam ends as per IS 13920 and use M25 concrete and Fe50 steel. So how to proceed? Again, the first part is very simple. We have this dead load plus live load effect. and that we multiply with appropriate factor, we get this value of the shear force. Now for a support section of the beam spanning between columns, we'll have hogging moment and sagging moment, right? For hogging moment capacity, top layer steel will act as tensile steel, bottom layer will act as a compressive steel. While in case of sagging, this is completely reversed. Now, we can calculate the area of the steel in top layer and bottom layer because that details are given here. And then next is find hogging moment capacity at the left support. So now we have clear span is 40 millimeter. So we can calculate the effective depth and we can also calculate this compressive force and tensile force, right? Then from there, we can calculate the location of the neutral axis. Then for the top steel, we can find out d prime. And then finally, strain in that compression zone, we can evaluate. Corresponding stress we can evaluate. Okay. Then here is the hogging moment capacity of the section. So this expression, if you recall, we encountered here. So we have all these hogging and sagging moments. So let us see how we can calculate this hogging moment capacity at support, and which is in this case 321 kilonewton meter. Then similarly, what we can do, we can also evaluate sagging moment capacity. Right, here you can see we have the moment capacity. So we have identified these moment components, right, at the different section. Now we apply the guidelines given in this IS 13920. So from sway to right, we calculate these shear forces using these expressions. It's very simple. We have already identified all the components. So we identify the shear forces. Then we have sway to left. For that also we find out this components. Now for left hand support, the design force is 150, as you can see. And for the right hand support, it is the maximum value. So it is 286. So if we start here, here is the shear force. So ultimately after comparison, we get that at the support A, we have the design force, and the right support also we have the design force. Then accordingly, once we have this design forces, we can redesign and check whether it is safe in shear. That exercise we are not doing here because it is exactly same the design against shear that we have discussed in detail. The main idea is to find out this value of the shear force from the ductility detailing point of view. So this is in addition to the design discussion that we had earlier, right? Now next is detailing of column. So for column, an inclined member in which factored axial compressive stress due to gravity and earthquake effects exceeds 0.08 FCK, the factored axial compressive stress considering all load combinations relating to seismic load shall be limited to 0.4 FCK in all such members. The cross-section aspect ratio, that is the ratio between smaller and larger dimension, shall not be less than 0.45. The minimum dimension of the column shall not be less than these two, 20 dB, where dB is the diameter of the largest diameter of longitudinal reinforcement bar in the beam passing through or anchoring into the column at the joint, or 300 millimeter. So that is the minimum dimension of the column we have to provide. So again, we have already discussed column design in detail, but on top of those, we have to also ensure that these guidelines are followed. Now, again, splicing is important, splicing of longitudinal reinforcement in columns. So the spacing of closed link shall not exceed 100 millimeter. The lap length shall not be less than the development length, which is obvious. Then not more than 50% of the area of steel bars shall be spliced at a section. This is also true. We have discussed in detail. Then lap splice shall not be used for bars of diameter larger than 32 millimeter, for which mechanical splicing shall be adopted. Okay. Then lap splices shall not be provided within a joint and within a distance 2D from the face of the beam. Right. So while detailing, these are the extra guidelines that we have to keep in mind. And lap splices shall be provided only in the central half of the clear column height. So this is important. This is the location, that is the central half of the column is the location where we should provide lap splices, right? Then from the transverse reinforcement, what are the guidelines? Let us quickly go through. Transverse reinforcement shall consist of a closed loop. We should not have any open loop, which is obvious because if you have an open loop, that will not provide sufficient confinement of the longitudinal bars. The closed link shall have 135-degree hook ends with an extension of 6 times its diameter, but not less than 65 millimeter at each end, which are embedded in the confined core of the column. Okay. Recall that ends, which actually, these are the ends. So here we have to keep in mind of this additional guideline for detailing. For rectangular links, the minimum diameter permitted for transverse reinforcement bars is 8 millimeter when diameter of longitudinal bar is less than or equal to 32 millimeter, 10 millimeter when diameter of the longitudinal bar is more than 32 millimeter, and the maximum spacing of links shall be half the least lateral dimension of the column except where special confining reinforcement is provided. Okay. So these are the additional guidelines. Now let us quickly go through the diagrams. These are some of the schematic diagrams as you can see on your screen. The maximum spacing of parallel legs of link shall be 300 millimeter center to center. The cross tie shall be provided if the length of any side of the link exceeds 300 millimeter. As you can see, this distance here it is 300 millimeter. So if you have more than that, we have to provide a cross tie here. The cross tie shall be perpendicular to the side that exceeds 300 millimeter. Hook ends of the hoops and cross ties shall engage peripheral longitudinal bar. Again, this is important because that is the sole purpose. If you have a longitudinal bar here, it should properly engage that bar. Okay. Alternatively, overlapping hoops links may be used instead of a single hoop with the cross tie. As you can see here, we have the detailing shown here. As you can see, consecutive cross ties restraining the same bar shall have 90-degree hook on opposite sides. Okay, so this is again important. From the detailing point of view, cross ties may be of the same or smaller diameter as the hoop bars, right? Preferably same diameter. We always recommend same diameter as we have for the hoop bars, right? Okay. Now comes, this is very important, strong column and weak beam. Okay. So when you have a frame structure, say if you have a frame like this, say this is a frame, and when we design, we have an earthquake shaking. Obviously, there are some load over these beams which is transferred to the column. Then this load is transferred from beam to column and finally to the footing, right? Now, when we design these corners, these junctions are important where beam meets column. Now, if we design a beam which is very strong, then obviously there will be more probability of having failure at the column. and if the column fails, obviously the entire structure will fail, and that therefore we will not go for a weaker column and stronger beam. Instead, we will always have a strong column and weak beam. As you can see here, each beam column joint of a moment resisting frame, the sum of nominal design strength of column meeting at the joint with nominal strength calculated for the factored axial load in the direction of the lateral force under consideration, so as to give least column nominal design strength along each principal plane shall be at least 1.4 times the sum of the nominal design strength of beam meeting at that joint. This is extremely important because that will ensure strong column with respect to a weak beam, and during an earthquake or extreme events, this will help us to deal with the overall safety of the structure under the extreme load. And for that, you can see the detailing guidelines. As you can see here, if you have a beam which is passing through a column, you can see the reinforcement details, while you have a beam which is ending in a column, you can see the different type of reinforcement, but more important is this guideline. Okay. So when we design a complete frame, in our discussion we design beam and column in isolation, but when you design a frame structure, ultimately where you have to design all the beams and columns, then at the joint you have to ensure that this criteria is satisfied. What is that criteria? The nominal strength should be in column should be at least 1.4 times the sum of nominal design strength of the beams meeting at that point. Okay, keep that in mind. This is extremely important, particularly during the event of earthquake or extreme forces acting on the structure. In our design, we separately consider beam and column design, and that's why these issues do not appear. But when you design a complete structure, you have to ensure that these clauses are also satisfied. So design shear for column ductile detailing. Again, this is important. Recall, for the beam we have already discussed. Similarly, for column also, the same frame will sway to right or sway to left, and accordingly we have to find out the shear force acting on the column. So design force, shear force demand in column shall be more than larger of this. What is that? First one is again linear analysis that we have already done. Then factored equilibrium shear force demand when plastic hinges are formed at both ends of the beam given by this. So from there we have seen for beam how to calculate the design shear force, and here also we repeat the same procedure, ensuring that we have a strong column and weak beam here. Okay. So now let us see again another problem. So a beam is framing into a column of clear height 4 meter on opposite faces. The reinforcement provided in beams at the joint face is as shown in the figure. Determine the design shear force in the column using capacity design provisions of IS 13920, assuming plastic hinges form in the beams framing into the joint. Use M25 and Fe 500 steel. Now, we have the same section for which we have evaluated hogging and sagging capacity. Now we have HST, height is 4 meter for this column. Then using this expression, we can find out shear force when we have sway to right and shear force when we have sway to left. In this case, we have the same values, and you see we can evaluate the shear force that way acting in the column. Spatial confining reinforcement. Spatial confining reinforcement consists of closely spaced hoops and cross ties provided in critical regions of columns and beam column joints. The aim is to provide ductility and energy dissipation. We'll see that in a minute. Why spatial confinement is needed? When column undergoes earthquake shaking, again recall in our design discussion, we never encountered this kind of situations where we have the complete structure undergoing some earthquake shaking. Okay, that is normally covered in advanced design courses where we consider earthquake force and we do a detailed analysis and we see how a structure undergoes deformation during an earthquake shaking. But for the time being, when a column undergoes earthquake shaking, large compression strains develop at potential plastic hinge regions. The concrete tends to crack and spall, and longitudinal bars tend to buckle outwards. I have already shown you some of the photograph earlier. Without adequate lateral restraint, the column can lose load carrying capacity very quickly, and this is the junction which is extremely important. So special confining reinforcement is therefore provided to hold the concrete together, delay crashing, prevent buckling of bars, allow the members to sustain large deformation. Recall, that was the main objective of this entire discussion. We should have large deformation before collapse. We'll see what are those special confining reinforcement, but before that, special confining reinforcement shall be provided over a length of L0 from the face of the joint towards the midspan of beam, okay, and mid height of the column. So if we have a beam column junction, so from this face up to this direction, length of L0, L0 is not less than larger lateral dimension of the member at the section where yielding occurs, 1/6 of the clear span of the member, and 450 millimeter. Okay. Then spacing not be more than 1/4 of minimum member dimension of the beam or column, 6 times diameter of the smallest longitudinal reinforcement bar, or 100 millimeter. Okay. Now the cross section of bar forming links or spiral of at least circular links, and you have the area of the bar given AS. So rectangular link will have AS as per this word. Okay, now let us see the detailing. Here you can see, which actually shows the detailing of beam column joints, and here you can see confined joint with beams framing into all four sides confining reinforcement. So here you can see this is extremely important. Okay, this is the region where we should have this additional bars holding the column, and that will prevent, recall the photograph I showed you, that will prevent the buckling of the members at this location. Now here you can see special confining reinforcement and the length over which it has to be distributed. Right? Then we have two different types of beam column joints. Here the column is having a beam which is spanning on either side. However, here we have beam which is actually ending on this column. So the rebars, as you can see, it is going here. Again, we have to ensure this development length plus these additional links here, and along with the special reinforcement for the proper confinement. The idea is that this column, the stiffness of this column, this section and this section will be much more compared to the beam. We should have a weak beam. If the plastic hinge occurs, it should occur in the beam so that we have the frame which is intact and the structure will undergo large deformation. Right. Finally, special confining reinforcement for the footing and the column. So let us see what are the guidelines. When the column terminates into a footing or mat, special confining reinforcement shall extend at least 300 millimeter into the footing or mat. As you can see here, it should be at least 300, if not more than 300. Okay. When the calculated point of contraflexure under the effect of gravity and earthquake effect is not within the middle half of the member clear height, special confining reinforcement shall be provided over the full height of the column. Okay. And then finally, special confining reinforcement shall be provided over the full height of the column that has a significant variation in stiffness along the height. This variation in stiffness may result due to abrupt change in cross-section size or unintended restraint to the column provided by stair slab. Okay, these are the special locations. So we have, if you have stair slabs, that actually provides, or mezzanine floors, plinth or lintel beams framing into the columns, these are actually provide additional restraint, and for that we have to provide sufficient amount of special reinforcement. And of course, if you have RC or masonry wall joining the column, same situation may arise. And under these situations, we have to provide special confining reinforcement as per the guidelines that we have already seen. Now, for this footing, again, recall, we have to check this development length of these bars. Development length of this bar, these are dowels. And then we have to have additional confinement so that particularly during earthquake, when there is a shaking here at the base and the column also sways on either side, there should be a proper load transfer between the column and the footing, and that will only be possible through proper confining of concrete so that the steel rebars are intact and it can experience large deformation without buckling at this critical location, right? So these are the guidelines that we have for ductility detailing. This is on top of the design guidelines that we have already discussed in detail. So with that, our RC design part completes of different components. Now in the following week, we'll see different structural components. So we will use the informations that we have learned through this design lecture series of beams, slabs, columns, and footing. And then following weeks, we will take different special structures, how we can design those structures that we will see in the following weeks. But this last lecture of this week is extremely important. So for the ductility detailing is concerned, and it is extremely important to ensure overall safety where we expect the structure should undergo large deformation before finally it collapses. So it ensures the safety and it has all these advantages that we have already discussed. Go through these notes and particularly this code IS 13920 and see what additional requirements are there on top of the design requirements that we have already discussed. If you have any doubt, do let us know through emails. We will clear your doubt. Thank you very much.